I'm just beginning with a couple of slides that really repeat what our president has been saying. An amazing observational career. They're a really impressive pair of binoculars. That they look like they started life on the bridge of a battleship. I've no idea where he got them. Yes, and this is the slide. There's a picture of Peterborough Cathedral. It's quite an amazing building and worth visiting in its own right, but certainly have a look for the plaque if you're ever there. The general nature of these talks is that they focus on a theme of observation. So I thought I would try and continue that by talking about my spectroscopist's journey. This is the spectrally themed outline of the talk. I'll begin at the beginning, obviously, then talk about photometry, which I did first, then spectroscopy, and then say a bit about what you can really learn from spectroscopy. Then go on to talk about the more personal sides of places I've been, people I've met, projects I've been involved in, and then finish with a few recent developments. So my astronomical journey began in my early teens with this cardboard tube. It had a small achromatic lens in it and a microscope eyepiece, bought for a princely sum of 11 shillings and sixpence, which is just under 60p. So that was quite an economic investment, shall we say. I mounted it on an extremely shaky homemade tripod. My woodworking was not up to very much, but it certainly let me see the first views of things like the moon and the planets, star clusters. I was an avid reader of Patrick Moore's books from the local library. I'd probably read several of them more than once. Watched the sky at night, which was in its relatively early days then, and joined the Astronomical Society of Edinburgh at Calton Hill Observatory, is where I lived. That's a picture of the observatory there on Calton Hill. And on 1967, I joined the BAA and have been a member ever since. The dome at the top contains a 6-inch Cooke reflector, which certainly gave me much better views of the planets than I was ever able to get through my little telescope, but it certainly whetted my appetite. So I had aspirations. Okay.
It's a Windows thing.
Yeah, well done.
Sorry.
Ooh.
Yes,
It's put me on to presenter. Okay. I had aspirations to buy a commercially made telescope, as one always does at that stage in one's career, such as this 6-inch Newtonian, which I drooled over in the Fuller Scopes catalogue until I looked at the price. If you can maybe just read it there, it's £58, 19 shillings. Now, that doesn't seem like a lot now, but in today's money, that was equivalent to about £1,000. It was certainly well beyond my means, my capability. So I decided to do what a lot of people did in those days, many of you probably have done, which was to grind and polish a mirror. I chose an 8.5-inch mirror. It turned out reasonably well, although I don't think I ever got rid of the turned down edge that it had. But I built a Foucault tester to test it. I used the book by Howard, which I found very good. It gave good instructions. When it came to mounting it, I followed some advice in a book by Jean Texereau on how to make a telescope and built myself a large English mount. I built it, the telescope went in a wooden tube and I had to build something pretty massive to carry it. And all I could do in those days was woodworking. So it ended up in an English mount. It was very much like an animated coffin, if you can imagine it. Swinging it around the sky. I have no idea what the neighbors thought of this. And I built myself a runoff roof observatory. The lesson I learned in those days doing all that was keep it simple. I was far too elaborate. I built something that ended up being a bit of a nightmare. I hate to think what my parents did with it when I finally left home. Anyway, that was their problem. I learned my way around the night sky with the help of Norton's Star Atlas. This was epoch 1950. Oh dear, 1950 in those days, so it's going back a bit. I used it to find things in the sky, and particularly, for example, Halley's Comet. I would draw little marks and lines on the chart where I was looking, and eventually, at the very end of that line, I picked up Halley's Comet for the first time in November, 10th of November, 1985. But eventually, I migrated to commercially made optics because I didn't think I was really ever going to perfect the art of mirror making. So I bought optics from actually Beacon Hill telescopes and mounted it in a Dobsonian style of mount, which was becoming really popular. I subscribed to a magazine, American magazine called Telescope Making. Some of you may remember that, which ran to many years, and I've got a complete set of it, which I'd be happily to donate to an organization that would look after it. I use this to make visual observations of the moon, planets, many Messier objects, but I suffered from a problem that many of you may have found, that the novelty of looking at the same object again and again does start to wane. They don't look very different from night to night. M42 was the same tonight as it was last night. And then I discovered photometry. For me, this was a light bulb moment. I heard about CCD cameras, and rather being limited to subjective visual observations, I could actually measure things, and measurements produce data, and data is what you need to do science. That appealed to me. My background is I was a physicist, so I was really looking for the opportunity to do some science. And I'm afraid the pursuit of quantitative data has really driven me ever since, sad though it may be, but true. I decided to join, to concentrate on measuring variable stars and joined the BA variable star section. This was my first camera. It was a Starlight, very early Starlight Express camera. I've been a loyal user of Starlight Express. I think they make excellent cameras. It's interesting that the cost is not increased hugely in terms of real cost of a camera. It's just the chips have just got enormously much bigger. I put my telescope, my trusty 10-inch telescope, on a permanent equatorial mount, which I really had to do to take long exposures. I bought a book by a Frenchman called Christian Buell that I hadn't heard of, but it was a really interesting book on CCD astronomy. And I subscribed to another American magazine series called CCD Astronomy, which didn't last very long, but it was interesting. And I've got a lot of those as well. I bought Richard Berry's book. Some of you may have bought this a few years ago, and started to do photometry using the software that came with it called AIP for Win. Came on a CD at the back. It was quite a steep learning curve because you have to learn lots of things like how to make darks, how to make flats, how to incorporate them in your analysis. But basically, measuring the magnitude of variable stars is pretty straightforward. You take an image of a region of the sky which contains the variable you want and a number of other stars whose magnitudes are already known. You just measure by putting circles around them with the software of the star, measure how much light there is in each circle, do a bit of calculation, and you can work out what the magnitude of your variable is. It's known as differential aperture photometry and is the basis for most photometry that amateurs do these days. But if you also incorporate photometric filters of different photometric filters, you can measure the color of stars. So you can start to do quite useful scientific work with that. Because I'd gone through the learning process and taught myself, and I was encouraged by Roger Pickard, who was the director in those days of the section. And I wrote a beginner's guide to measuring variable stars with a CCD camera. This was published by the BA. I don't think it ever became a hot seller, but I hope one or two people found it useful in getting up to speed with photometry themselves. I'd written a little spreadsheet to help me, and Andy Wilson took that and created the BA photometry spreadsheet from that, which I think is still available and people still may be used by people who are doing their own photometry. And Andy also set up an excellent photometry database for the BA in the early days. So over the last 25 years, I've measured more than 500,000 images, and the data from the measurements from those have gone to, almost all of them have gone to one of the various databases, either the BAA or the AAVSO. And as it turned out, the skills that I was learning during photometry were going to prove useful later on in the journey I was making. And of course, I had to buy myself a bigger telescope because you can never have enough telescopes as a retirement present. That was a 14-inch Schmidt-Cassegrain. And incidentally, I decided, keeping things simple, these telescopes were mounted under little roll-off sheds. They're about 4 feet cubed. and I still use that today. It keeps the telescope dry. I can be up and running in a few minutes. So the lesson of keeping it simple has stayed with me. So photometry can tell you a lot about the physical parameters of stars. If you measure the light curve of a variable, an eclipsing variable such as this is several nights' data all brought together and phased up. You can measure from things like the distance between the primary eclipses, the orbital period of the star. You can measure the relative diameter, the luminosity, temperature. There's quite a lot of information about the bulk nature of the components you can get from photometry. But photometry doesn't reveal everything. Here's a light curve of a pulsating supergiant, R Scuti. And you can see its magnitude changes over what, four magnitude in the course of that pulsation. But other than knowing it gets brighter and fainter, you don't really know what's going on. But when you take spectra of it, you find out that the spectral profile changes enormously. At the top of the spectrum, you're looking at a relatively hot star, maybe a G or K star type star, but by the minimum, the spectrum's completely changed. And what you're seeing is the spectrum of molecules, essentially titanium oxide absorption bands. So spectroscopy can start to tell you about the physical changes that are taking place in a star, which from photometry just gets brighter and fainter. So spectroscopy started to look like a really interesting thing to do. So I started investigating it. My first steps in 2012 were with something called a Star Analyzer 100. Anybody who's into spectroscopy has probably started with one of those. It's a transmission diffraction grating manufactured by Patton Hawksley, and it's a design that was effectively inspired by Robin Ledbetter, whose picture you see there, who's probably the earliest spectroscopist in the UK, and has for many years supported many people, including myself, in learning and climbing up the learning curve. He's done a great job for the community. And this is it's a good way of finding out about spectroscopy if it's for you, because you're going to have to learn quite a lot of other aspects of analyzing data. And you can decide whether without spending a lot of money, whether this is something you want to do. And it fits in a standard filter wheel, and it produces a spectrum of all the stars in the field of view. And that image is really a star field which happens to include the spectrum of Nova Delphini 2013. That's a really bright object. The zero-order spectrum is the white dot on the left. And what the grating does is spread the light out into a spectrum. And you can see there are a couple of bright spots within that spectrum. And by integrating across that band, you can produce a spectral profile in an image like that. And you can start to see that, okay, there's at least two bright emission lines in that spectrum. So it starts to get you hooked. But what you find fairly quickly is that these images are low resolution. The stars all crowd together on the image, and you've got a relatively high level of sky background. So to get better results, you really need to use a spectrograph with a slit, which isolates the star, only reduces the sky background, and you can potentially get much higher resolution, because the resolution is now determined by the width of the slit, not by the size of the star image in the sky. And just to compare the results, the top plot there is the one I showed you earlier of the Nova Delphini 2013 with the star analyzer. And below it is the spectrum you get with a spectrograph with a slit. The lines you can see are much sharper, but the purple one is just the bottom one expanded up. And you can see there's a huge amount more detail. You can start to see emission features from different lines in that spectrum. So there's potentially a lot more science available using a device like that. So the next step forward happened at Astrofest in 2013. I met this charming Frenchman called Olivier Thizy, who's also very persuasive, who worked for a French company called Chauliac, which was just starting up making spectrographs and bringing them to the amateur market. The picture is the team that was doing that. The chap sitting down on the left is Christian Buell. He's the one who wrote the book on CCD cameras, was now creating a market for spectrographs for the amateur market. He was really the brains. He's the design engineer behind this company. The chap standing up is Francois Corchard, who now runs it, and that's Olivier sitting down. So I was persuaded by Olivier to buy one of these spectrographs. I bought the Lisa, which is what you see there on the back of a C11. But by that stage, I'd bought another telescope. You can't have enough telescopes, remember. So I attached it to the back. The cutaway drawing shows you what's inside one of these. They're really quite complicated. They're very clever bits of both optical and mechanical engineering, which fold the light path around, deliver it to an imaging camera. But the slit is a reflective slit, which not only passes the light through the slit, but also reflects the surrounding field into a guide camera. So you can actually guide the mount by using keeping the star that you're taking the spectrum of in the slit. It has a resolving power, spectral resolving power of about 1,000. And all the spectra I'm going to show you on most of the rest of the talk were taken with that spectrograph on the C11. So spectroscopy presents another learning curve. However, the experience I got from photometry was very useful. I'd learned a lot of the basics about handling images and reducing noise in them, that sort of thing. But spectroscopy is definitely more demanding than photometry because you're spreading the light from a star that perhaps you could image relatively in a few seconds now into a long spectrum. So you need to expose much longer to record a good signal to noise. And that puts greater requirements on the instrument you're using. It has to be stable, it has to be able to guide and track very accurately because you've got to keep this star inside the slit on the same position, basically on the chip. And there are new techniques you're going to have to learn, things like guiding on the star in the slit, wavelength calibration and flux calibration. These are things I'll talk about shortly. And you've got to master new software. There is a huge amount of software available now to amateur spectroscopists. I've been using ISIS for many years, but I've used some of the others. They're all very good. They all have their own kind of learning curve to follow. But the nice thing about them is they're all free. You can download them. You don't have to pay for any of these things. And there are new problems you have to understand when you're getting into spectroscopy. And this little cartoon attempts to show you what the problems might be. Many bad things can happen to light coming from a star. Imagine your target is sitting in the middle of some kind of circumstellar cloud. The light gets out of the cloud. It has to pass through interstellar medium for maybe 1,000 light years, a long way, before it finally hits the atmosphere. So the last 100 kilometers as it comes through the damp, cloudy atmosphere, light is getting absorbed all the way through that process, and in the sky, background's being added. So your signal is getting a little bit fuzzier and messed around. Then the light goes into the telescope. That neatly removes the ultraviolet part of your spectrum. You then pass it into the spectrograph, and a CCD camera. They have their own spectral sensitivity. They record some wavelengths better than others. So you're losing light, there's instrumental losses in that whole process. And there's a little bit of noise gets added in the camera as well. So into the computer, you finally end up recording something that we call a 2D spectrum. It's basically an image with the spectral light dispersed across in a horizontal direction. What you actually want to know is what the spectral distribution of the light from that star was before it left the star itself, to produce a spectrum that you can actually ideally measure and get some science out of. So wavelength calibration is the first thing you've got to do because you've recorded the spectrum on a camera with pixels across. You've got x coordinates of the pixels all the way across. But what you want to do is turn that into a wavelength scale. You do that by taking an image of a light source. Usually it's an argon neon lamp, which has got lines at well-defined known wavelengths. So you can work out the relationship between the x-coordinate of the line and its wavelength. And once you've done that, you can take the spectrum you've measured of your target, like the one at the bottom, and you can calibrate that in angstroms horizontally. So you've now found a way of wavelength calibrating. The next thing you need to do is flux calibration. It's because remember, we were losing light as it went through various stages in the process and altering its spectral profile from what might have been originally emitted. So the way you deal with that is you take a spectrum of a star whose spectrum you really know what it should be. You record the spectrum, the one in blue. You know that for this reference star, you know what the black spectrum actually looks like. So you can work out what the correction you have to apply to your measured spectrum to get the true spectrum. And once you've done that with a reference star that you knew all about, you can turn to the target star, you measure it, and you apply the same correction. And that's how you would eventually get to an accurate recorded spectrum emitted by that star. And a refinement, that's normally in some kind of relative flux units on your vertical scale. But what you really want to do is, if you're going to do science with it, is you would like to turn that into an absolute flux scale in physical units of spectroscopists use ergs per square centimeter per second per angstrom, which is a little bit old-fashioned these days in the world of standards, but that's what we do. But why would you want to do that? Why would you want to turn it into a spectrum calibrated in physical units like that? Well, there are several reasons you might want to do that. You can then compare your results with somebody else's. It's the same reason we use filters and photometry to reduce everything to standard magnitudes. It means you can compare your results with what other people are measuring anywhere in the world and build up a consistent set of data on a star. You can also measure the absolute flux of different lines. You have emission lines and absorption lines in the spectrum of a star. And these are telling you something about the physical conditions in the star. So if you can measure them in real units and particularly monitor how they change, then you're starting to learn something interesting and potentially novel about a star that hasn't been very well measured before. Something I got particularly interested in was looking at the pulsation of Mira stars. And that allows you to monitor the physical changes that are taking place in the star over time. And your data can be useful to somebody else. You record this data, you send it to a database, and somebody comes along in maybe 5 years, next year, whenever, with some kind of physical, astrophysical model that predicts what that star should be doing. If your data is there as a ground truth, it allows the calibration of models and testing of models against data. So you're producing data that's potentially going to be long-term scientifically useful by doing that. I also needed to learn a lot about stellar astrophysics in this whole business because I was new to this area. There was a lot of information there that you have to pick up. The groundwork in the area was really laid a long time ago by this team of ladies known as computers at Harvard College Observatory. These included people like Williamina Fleming, a girl who came over from Dundee to work as a housekeeper from Edward Pickering, ended up leading that team and developing some of the fundamental standards in spectral classification. And other people like Annie Jump Cannon. If anyone's interested in this, it's a fascinating story. I can strongly recommend the book called The Glass Universe by Dava Sobel. It's definitely worth reading. They studied glass plates of stars were taken with typically with objective prisms on the front of refracting telescopes, and they got plates which look very much like the sort of things I was showing you with a star analyzer. But now they were much more detailed, much higher quality, and they were able, by studying these and how they change, how stars evolved over time and changed over time, they developed a classification of spectral types. It was subsequently refined by Morgan and Keenan, and that's why we call it the MK system today, but it largely is based on what these computers developed simply by observing and inferring and deducing what they were actually seeing. And just to give you an idea of what the range of spectral types kind of looks like in a colorful, pretty way, these are stars which are all stars in the winter hexagon. So it's easy to take a set of spectra of these over a couple of nights. Down the left-hand side, you can see the different spectral types. O and B often get lumped together, OB as a class, and then there's A, F, G. The Sun is a G2 star. There's subdivisions of each of these classifications, and then down to K and M, where you get Miras. and it's really a temperature scale, because the OB stars are very hot, and most of their emission comes in the violet end, the deep blue, ultraviolet. The red ends are really faint, and as it goes, the temperature drops, the light moves more and more towards the red end, and by the time you get to stars like Betelgeuse, the light is primarily coming out in the red, and it's now structured with lots of molecular lines, which you don't see. The really dark hydrogen lines, hydrogen alpha and beta, they come and go. They're strongest in A-type stars, and then they gradually fade. So by measuring these lines, you can learn a lot about the spectral type of a star and watch how, in some cases, how that varies over time. Now, if you're on a journey and you're exploring some new territory, you need a map. And in this business of spectroscopy, it's the Hertzsprung-Russell diagram that's really the best place to work with. It's a plot of stellar luminosity vertically versus temperature or color or spectral type, which are really synonymous in the horizontal direction. There are also luminosity classes in that which divide spectra into a number of groups. The main sequence are usually called, have the letter Roman V, 5. The giant stars above to the right are type 3, supergiants are 1, and then down the lower left is the dwarf stars. And the stars are formed and arise on that main sequence, largely determined by their mass. The most massive stars are those at the top left, and by the time you get down to the bottom right, you're dealing with really faint, small stars. They're dwarf stars, really. But there's many, many more of those. Those are the most numerous stars in the galaxy. And as stars evolve, they live much of their life on the main sequence, but then they gradually start to evolve. And that typically means they're rising up towards the upper right of the diagram. They may turn into red giant stars, lose their outer atmosphere in a planetary nebula, and end up, the core of the star ends up as a white dwarf. So the lifetime of stars is charted out in the Hertzsprung-Russell diagram. So what can we learn from spectroscopy? I've got to show you some examples of the application of spectroscopy to learn a little bit more about a few different kinds of objects. We can understand why comets appear green. If you see color images of comets, they almost always have a green nucleus. And the reason for that is, the secret of that is in the spectrum. If you look at the spectral distribution of the star, there are a number of emission features. There's a really bright one, usually in the deep ultraviolet, the deep blue, a line of cyanogen. The reason you don't get much light from that in the images is that cameras are very insensitive at those wavelengths. And it's actually the middle part of the spectrum where there's a green line from diatomic carbon that really dominates the light from a spectrum. So it's because of that particular molecule in the star that you tend to see them as green. But you can see from the spectrum, I've labeled some of the other molecules that are present. There's a lot of radicals in. It's a pretty complicated chemical mix in a comet. I imagine it would smell pretty horrible if you put your nose into it. So the other thing, we can reveal the nature of planetary nebulae. This was a problem a long time ago. These were called planetary nebulae by Herschel, but people didn't know what they were. Fuzzy objects. Were they unresolved star clusters, or were they something else? And it was really William Huggins turning his visual spectrograph, and that's a picture of it. He had to look into his spectrograph. The cameras didn't exist in those days. He looked into it. He observed the spectrum of the NGC 6543, what we would call the Cat's Eye Nebula now, and revealed it had emission lines. And that immediately told him what he was observing was not a crowd of stars, it was a glowing gas. This nebula was actually gaseal. He tried to work out what he was seeing. He identified one line, the one on the left, was as hydrogen, and he was dead right on that. But with the others, he was really struggling. And for many years, it was thought that this was a new element, which he called nebulium. It was actually about 60 years later before it was recognized that these were something else by Ira Bowen. There's a nice picture by Kevin Garfield. This is what it looks like. It's actually quite greeny blue, and you'll see why in a minute as well. This is a spectrum of what it looks like. And down at the bottom is William Huggins' little visually recorded hand-drawn spectrum. And above it is the spectrum I got with the LISA. And you can see his 3 lines are very strongly recorded there. And above them, I've identified what they are. And in fact, they're what we call forbidden emission lines of oxygen, of doubly ionized oxygen. Forbidden because they were not detected and recognized on Earth, because they can only exist in an extremely tenuous gas, because the electron level, which generates by decaying that line, just doesn't last long enough. By collision, it's destroyed in any kind of even a vacuum on Earth in a laboratory. But in the atmosphere of a planetary nebula, these lines exist, and they're formed, and they're very strong. And you can see they're sitting around 5,000 angstroms, the 2 really bright ones, and that's what contributes to a lot of the color that you see. It's also why, if you want to look at these things and observe them, you get an oxygen-3 filter, because it neatly cuts out the emission at those wavelengths. But there are a number of other emission lines there, and I'm just going to highlight 2 little groups. On the left, there are actually 3 oxygen 3 lines there. One is very faint, but it's detectable in the spectrum. And if you amplify the spectrum, you can detect and measure all of these 3 lines. And over at the right-hand side, just to the right of hydrogen alpha, there are 2 lines of silicon 2. So what can you do with these? Well, you can use these lines, because we know from atomic physics what is going on in the process that creates these lines. The first thing is you just simply measure the wavelength of one of them. Take the brightest one of oxygen-3 at 5007. You measure its wavelength. You compare that with what you know is the rest wavelength of oxygen, and you find that it's actually has a wavelength shift, which means it's coming towards us at about 53 kilometers a second. So you've just been able to measure from that spectrum what the velocity in space relative to directional velocity towards us of that nebula. It doesn't tell you about the lateral velocity, but it's a radial velocity. And we know that from basically atomic physics that by measuring the ratio of the intensity of these 3 oxygen-3 lines, you can deduce the electron temperature, which gives you an idea of the kinetic energy of the electrons within the gas. Because it's basically a plasma, because it's ionized by a very hot star in the center. And the 2 silicon 2 lines I pointed out on the right-hand side of the spectrum, knowing the temperature, you can work out what the electron density is from that. So these are calculations that you can do with a spectrum you can measure in your back garden. And if you then look at what the published values are for these, they're remarkably close to what you can simply measure. So the kind of equipment we've got is certainly capable of scientifically interesting measurements that you can make. I thought it was also interesting to note that the NGC 6543 is about 3,300 light years away. That meant that light we're now looking at left it during the Bronze Age. So it's a bit of a time shift. We're looking back in time. We can measure the expansion of a nova explosion. A nova is when you get material in a binary system, matter, hydrogen mainly, transfers from a main sequence star onto the surface of a white dwarf, and often via an accretion disk around it. But eventually, that material builds up on the surface of the white dwarf over possibly hundreds, thousands, maybe even millions of years. But the density and pressure increase to a point that triggers a thermonuclear explosion. And what that does is it blows the layer that is accreted on the surface of the white dwarf. It just blows it off into space. And this is a spectrum of a nova in Cassiopeia in 2021. And the lines have a peculiar shape because there are the emission lines that you might expect to get from hot glowing hydrogen gas. But to the left of each line, there is a dip. And we call it a P sigma dip because of P sigma, there's the prototype star in which this behavior was first seen. And what they are is it's absorption in the shell. There's this shell that's exploding. It's coming towards you. It's gradually absorbing some of the light, but that absorption is blue shifted. So you get this blue shifted dip on each of the lines. And the nice thing about that is you can measure the depth, the point at the bottom of each of those dips, and you can measure the wavelength shift of them, and you can work out what is the expansion velocity of this explosion. And this thing comes out at about 1,400 kilometers a second. And if you go and look up the astronomical telegram that was issued just after this explosion, you find that the professional observers were measuring this at about minus 1,500 kilometers a second. So maybe I was a day late in actually getting the data. But it's something you can measure of an event so when T-core Bohr goes off, this is what you do if you've got a spectrograph. Okay, you can measure the radial velocity of the active nucleus of a Seyfert galaxy, M77. If you look at the spectrum, there's a lot of emission lines as what you get in the active nucleus of one of these galaxies. But you see that each of them is shifted to the right, is red shifted compared to the rest wavelength of the line, which is drawn as a dotted red line. And if you measure the redshift of each of these lines, take an average, you can work out that its radial velocity is about 1,100 kilometers a second going away from us, and that corresponds to a redshift of 0.0037. Okay, so that you've measured that. You go and look in the NASA extragalactic database, NED, for this star, and it tells you that Z is 0.00379. So just from, again, simple measurements of the spectrum, you're able to measure things like the recession velocity of a really active galactic nucleus. The other thing you can do with a spectrum of that object is, there's a nice picture of it that I got off the gallery, the BAA gallery. So this is the object that we're talking about. And this is a spectrum, and I've highlighted just a section of the spectrum which around the H-alpha line. It's an H-alpha line and a couple of lines on either side of it of nitrogen, forbidden lines of nitrogen too. If you just look at that particular section of the spectrum, which I've blown up in the top of that, you can see that I've marked up which is the hydrogen alpha line, and the two faint ones are the nitrogen lines on either side of it. But you can immediately see that there's they're staggered. One is to the left of the bottom one is to the left of the right one. And what that allows you to do, if you work out, at all the x coordinates, the y coordinates vertically, if you measure the wavelength shift of the hydrogen alpha line at lots of different y coordinates, you can gradually build up a profile of the velocity of these lines. And if you just find out where the average is, if you like, which would be the center, the recession velocity that we know what it is, we've just measured it, of the center of the galaxy, you could start to build up what looks like a velocity curve of the rotation of the galaxy. So again, this is something that people in the early days of spectroscopy were measuring these and finding out things like rotation velocities of these galaxies. You can do this in your back garden. The picture just shows you where the spectral slit runs across the top of the object. And this is 47 million years ago. So that's what we would call the Eocene on the Earth, that era. There were mammals wandering around on the Earth, early mammals, as life left us. So we're starting to go really quite far back in time. And then if you go really to something a long way away, like the quasar, one of the really bright quasars, like 3C273, which has a supermassive black hole at the center. And this caused some problems in the early days. People measured the spectrum, which had three clearly detectable, well, in a professional spectrum, you get a lot of clearly detectable emission features, but with my little LISA and my C11, I was getting three quite strong emission features, which caused them problems when they first saw these, because they didn't relate to any known wavelength, and it was only later, or after a lot of thought, that they realized these were red-shifted versions of lines like the three red dotted lines that were being redshifted by an enormous amount by a redshift of 0.158, which is the average of these 3 lines, means that this thing is receding from us at over 47,000 kilometers a second. Now, if you take a mean Hubble constant, and that's a pretty nebulous concept because nobody really agrees what it is these days, but if you take an average value, you can get a Hubble distance to this of about 700 megaparsecs. And that's pretty close to what you'll find in the professional literature. And what's worth thinking about is the light was been traveling from that object for 2.3 billion light years. And that's back, it left during snowball Earth, when the Earth was just covered by ice. So you're really looking back a long way in time when you look at things like this in the far parts of the universe. So let's moving on to talk about places, people, and projects. And I'll have a drink. One of the things I did in the early days was go to the OHP, that's Observatoire de Haute-Provence spectroscopy workshop in 2015, and then I went 4 years later. This is organized at OHP, which is the place where the first exoplanet was measured by Mayor and Queloz. It's organized by Francois Cochard. It's largely for the French community because spectroscopy has really kicked off in France, above all countries really in Europe, largely due to the work of people like Christian Buell, developing affordable spectrographs for the amateur market and then turning them into commercially available high-quality products. So this is at the workshop, a lot of French amateurs bring their spectrographs and set them up in the field around the observatory, and we all eat together, and I practice my schoolboy French very badly, but a lot of them speak English, as you might expect. So it puts us to shame in a context like that. I met Christian Buell. He was a charming guy, a really nice fellow. I also met somebody called Steve Shore, who's an American who is a professor at Pisa University, but spends a lot of time helping amateurs. He comes along and gives a lecture course every year at this. That's one thing I could understand in English very clearly. So OHP was a great place to get to know some of the people whose emails you've picked up in email groups, and just get a bit of inspiration. So it's a great type of environment to be immersed in for 4 or 5 days. And it was discussions at OHP with various people that really convinced me I should learn Python. In my early days as a physicist, I'd done a lot of Fortran 4 programming. It's what you did. I'm that old. I then, career, as you do, you move on to managing people who go on having the fun of programming and you're not doing it. So it was a great attraction to go back to doing something I really had enjoyed doing. And Python is really the ubiquitous language of astronomy these days. It's largely because something called the AstroPy project has been developed. It's a community effort to develop a common core of packages for astronomy in Python. Almost anything you want to do in any algorithm you want to implement in Python, you'll find, you can Google it and you'll find something you can download, and you can do things like reading and writing FITS files, which is the canonical format, barycentric correction, cross-correlation, querying databases, wavelength calibration, solving orbital binary stars. I've done most of these things by just picking up packages and building them into programs that I've written. So it's relatively easy once you get understand the basics of the language, how you can start leveraging it to do a lot of useful, interesting science. Back in 2016, I was trying to get more people in this country involved in spectroscopy. So I had the idea, if I could persuade the BAA to stump up some money and also persuade Shellyak to give us a discount of this, something called the ALPI 600, which was a new spectrograph, less expensive than the ALV, slightly lower resolution, but very capable of doing equally good science. If we could get a project together, an initiative together, which would effectively make these available to people at half the cost, that it would help to kickstart things. And we eventually managed to do that for 8 BAA members who had to pay half the cost, but they got the spectrograph. And we ran a training course at Kintbury near Newbury, and Francois Corchard came over and gave it. And I know some of the people in this room were on that course, and I hope you're all using your spectrograph still. I know many of you are. So that was a way of helping to encourage spectroscopy in this country. But I also got involved in this group, the Society for Astronomical Sciences. It's a pro-am group which has been running many, many years, holding annual meetings in California on the West Coast US on what they call small telescope science, which is a nice description of we tend to call citizen science in this country. Small telescope is slightly different to them. A half-meter telescope is what they call a small telescope. There's a lot of very wealthy retired people in the West Coast of America. I've been to this several times, got to know a lot of people, given talks at it. I was asked, I was doing this kind of spectroscopy evangelist sort of thing and it was interesting that spectroscopy is really not taking off in the US very well at all. There were not many people doing it. There were a few people who had been really dedicated and built their own spectrographs, but there was no real market for amateur spectroscopy. So I started sowing seeds there. I also sowed enough seeds that I've probably got about 10 BA members from people from these meetings who got sufficiently interested to join the BA as well. And I gave a 3-hour workshop on scientific analysis of amateur spectra to try and kickstart people. This was just before COVID. The slides of that you can still find on the BA website. Also mention, it was interesting, on the first one I went to, because this was held at a place called Big Bear Lake, which is quite close to Riverside, I was able to go along to the Riverside Telescope Makers Convention. And I remembered that well from the telescope making magazines that I bought and read. There were lots of articles in there, as there was in Sky and Telescope, of Americans who love building their own telescopes. And it was the first time I went, there were a lot of telescopes on the field that people had built. They were works of art, really. About 6 or 7 years later, I went back and I was very disappointed. There were very few homemade telescopes. There were a lot of commercial stands in tents selling Meads and Coronado telescopes. And so the do-it-yourself market has sort of faded away in America over that time. And just last year, I went to a European conference in Austria, which was specifically about pro-am collaboration in spectroscopy. And there were a number of American professionals came over and spoke at that. And it was a really good environment to discuss spectroscopy and what amateurs were doing and how that could be useful in a professional context. It was also another chance to meet like-minded people, apparently exclusively middle-aged men. This is, I mean, it's the same if you go to the conference in America. You have a room of 100 people and there might be 4 or 5 women in it. That was the way it was and probably still is. I think it's maybe getting a little bit better, but it's very much a retired male dominated community. They have the time, they have the money, and that's what it takes to get it. And most of them have some kind of professional background, which gives them the motivation and interest to get involved. Databases are really important in this. ARAS is a spectral database set up by Francois Tessier, who's done a great job over the last, 10, 15 years in really single-handedly setting up and managing a database and running an informal group of amateurs who contribute observations to this database. And there are now thousands of spectra in there, which have now been picked up by professional astronomers. If people get interested in a star for some reason, they go and look in the database, and very often there are spectra there which are very useful to do this comparison of models and that they may have of how they think these stars behave. This focuses primarily on symbiotic stars, which are really an interesting kind of binary with typically a dwarf, a giant star and a white dwarf, and novae, of course, which are always interesting. potentially. And in the UK, we have got, the BA has a fantastic spectroscopic database set up by Andy Wilson. Kudos again to him for doing this. And I really think this is the easiest to use amateur spectroscopic database. You can upload your own spectra without having to go through any validation or checking. And Andy checks that you know what you're doing up front, and then he lets you submit spectra to the database, and you can download other people's spectra. So if you've taken a spectrum of an object, you just want to check, does this look right? Have I processed it correctly? You can go to the database and find some spectra you can download, and you can compare it. And that is a great way of reinforcing your own knowledge and understanding. The spectroscopy discussion group is really interesting, and how this has evolved. It's really now become a worldwide online community of amateurs and professionals in spectroscopy, set up really initially under the auspices of the Society for Astronomical Sciences, but really triggered by COVID. Conferences were cancelled, people couldn't meet, people discovered Zoom and discovered that they could continue talking to each other. Woody Sims here, who lives near Phoenix, has done a great job in really taking this concept and turning it into a very vibrant spectroscopic discussion group, which meets every 2 weeks, fortnightly via Zoom. And we have a number of emeritus professors, that means retired professors, in astronomy who participate very actively in the group. Particularly noteworthy is Richard Gray and Chris Corbally, who are the co-authors of a group on stellar spectral classification, what we fondly refer to as the Bible, because it really is the definitive book on how to interpret spectra. It's a bit of a joke in a way, because Chris Corbally is actually Father Chris Corbally, because he works at the Vatican Observatory. He doesn't seem to mind the fact that we call his book the Bible. Also, there's Hans Martin Schmidt, who's a German who did a lot of early work on symbiotic stars, and Steve Shore popped up again in that group. He is probably the world expert on novae, and he's great at critiquing what we do, telling us what we're doing wrong, and pointing us in the right direction. So it's great to have a context like that when you can regularly show the sort of results. We bring beginners in. I mean, it's getting huge now. It's stretching the limits of what you can do in Zoom, but beginners can come along and say, look, this is my first spectrum. People can say, yeah, that's great. And maybe if you did this, you could make it better. And it sort of bootstraps people into the community. Publication is crucial, I think. It's vital. If you don't publish your data and your results, as far as the rest of the world's concerned, you may well not have bothered doing it. It may have given you some personal satisfaction, but that data isn't going to be of use to anyone after you've given up and gone. So uploading your data is one way of facilitating publication of your data, of a form which is then available to other people. There are several referee journals which will publish happily papers from amateurs, and our own journal is certainly one of those. The AAVSO journal will also do it. I've published in both of those. Professional journals will publish amateur papers, but they do set a higher bar, because what they're looking for is not just a discussion of the data. They want physical interpretation. They want to understand why your data is actually advancing knowledge in some way in the field. But another way of doing this is if you've got a professional collaborator, they often have more ready access to the professional journals, and they can open the door to co-authorship. Often professionals who are interested in a particular star, particularly if it's not some really faint, mysterious quasar or something, if it's a fairly ordinary star but maybe a little bit peculiar, they find it very difficult to get telescope time on a professional telescope, because it isn't kind of sexy scientifically to the professional community. But by talking to amateurs, they can get us to go away and collect the data that then forms the basis of a paper. 3 examples that I've been involved in recently over the last 2 or 3 years are those papers there. 2 were authored by Richard Gray, and the third by James Jackman, who was at Warwick emigrated to America and went to work at a university in Phoenix, and helped us develop a paper on studying flare stars. So, and there's a lot of the majority of the authors, co-authors in these papers are amateur observers. You don't just have to do pro-am, you can do am-am collaborations, because I've helped to get small groups together to study particular things like eclipses of a symbiotic star, or flares of one particular star there. And we published them in the AAVSO journal. That tends to be a better place to put some of this sort of work than the BAA journal, because it involves lots of tables of data. And you'll probably know as a BA journal reader that tables of data is not the most exciting thing to see when you open the journal. The AAVSO are happy to take that sort of stuff because they publish online, they don't publish a printed journal, so it matches better against the sort of thing they're doing. And I've also published papers myself in the AAVSO. I got interested, as I mentioned earlier, in MIRAs, so I've been doing a series of observations of different types of MIRAs, and just decided to write them up and publish. This sort of thing you can do if you get interested, because in spectroscopy you're ploughing a slightly newer furrow than maybe just in spectroscopy, in photometry. Right, recent developments, very quickly. Christian Buell's been an innovator for many years. He conceived of something called a StarX, which is a low-cost 3D printed spectrograph. And you can build that either for low or high resolution. It's considerably less expensive than something like a Shell high-res. You can buy the optical components. You can buy 3D printed spectrographs, 3D printed components for it. And this is mine, laid out on the kitchen table, all the things that I needed to build a StarX. Camera, Starlight Express camera, optical parts, and as they say at IKEA, and this is what you get. You put it together, you put it on the back of the C11. I can swap this over with the LISA. I measured the 3 stars in the summer triangle and proved that this really did deliver a spectral resolution of 10,000, as it was supposed to do. I contributed on a pro-am project, which gave me a really accurate radial velocity curve with an accuracy of about 2.4 kilometers a second, which was useful enough to help them with this binary star, which might have exoplanets around it. Just to finish, before Janice jumps up, Christian has another trick up his sleeve, something called the SolX. It's a high-resolution spectroheliograph using the same 3D printed parts. So you have essentially the same components, but you don't need a cooled camera, you don't need a guiding module, a guiding camera, or a calibration module. What you do is you put that together, you put it on the back of a small refractor. It gives you a very high resolving power, about 40,000. The cost is about £600 for the actual spectrograph itself. You need a telescope, obviously, to put it on, but you may well have one of those. This one is on a small TeleView Pronto. You need a neutral density filter on the front, otherwise, if you don't want to melt the plastic directly, so you need to filter the sunlight a little bit. Simple CMOS camera. It's several times less expensive than a double stack filter, which actually has a lower resolving power. So it's a nice thing to have and to experiment with. The sun scans across the slip. SharpCap creates a video file. You can then process that with either JSOLX or INTI to produce a disk image. And basically, this is what you get. You take a series of images, you stack them with Astra Stacker, you sharpen them a bit with Photoshop or your favorite image processing software, and you get an image which the quality is limited by seeing typically. But the SolX has one further trick, 2 slides to go. It's one trick up its sleeve. By rotating the diffraction grating, you can image the solar photosphere in the wavelength of other spectral lines at no extra cost. And there is 2 images taken, one of hydrogen alpha, one of calcium K of the sun. And I think that's a good place to stop my spectroscopic journey. And thank you for listening and tolerating my self-indulgence.
Oh, that was excellent. I think we all were fascinated, riveted by your journey.
Go and buy a spectroscope.
Even if it's not your own particular interest, how you've got there and what you've done was fascinating. I would like to offer time for questions, but we are running a bit behind. So, you are the next speaker and you are here. You're just getting mic'd up.
Yes.
Are you able to use that to deduce anything about the rotation of the central?
You probably can, yes. There'll be rotational broadening in there. I've not tried doing it, but there's a lot of data in these slides, quantitative information in these spectra that you can use. If you know what you're doing. Again, you've got to climb the learning curve to know what to do. Okay.
Okay, whilst the next speaker, Dr. Malcolm Fairbairn, is being mic'd up, then
I can answer questions.
we can have a couple of questions. I will repeat the question rather than faff about with microphones going round. Any further questions? So,
you showed a supergiant there, RW. What constellation is that?
what constellation is the supergiant RW in?
Which W? Well, I showed you our Scooty. That was I'm not sure which star you're referring to.
I know what it was.
Yeah, I know.
No?
I'm not sure.
Any advice?
Constellation? No. Sorry.
Any other questions, ladies and gentlemen? No. Okay. Well then, I'll just say thank you again, David. That was fascinating. I have a couple of questions, but I think I'll keep to later.
You know my email address.
I do, and there's no mistake. Okay, thank you very much.